Welcome to my lecture on basically a recap of Chapter 3, but the main point of this is to recognize common discrete distributions. So perhaps I should put on this word. Well, then it goes off the screen, so I'll keep it as it is. But I'm going to quickly discuss the distributions. So we have a list of distributions, and they're kind of summarized on page 78 of your textbook, and these are the common situations. So they list the density, and it's pretty obvious if you have the density you can name the distribution. But what's given to you in the problem is not, hey, here's the formula, here's the density function. Instead, what's given to you is a description, and some of the descriptions include things like this. Okay. Another thing that's always given in the problem is the random variable. So that's critical to determining if the density function applies. So here I have my first random variable is the number of trials until the first success. And if you run through this, it could take a lot of trials until you get your first success, and therefore there's not a fixed number of trials. Now in the problem there needs to be given a fixed probability of success. Okay, and I have the mean listed here. One other thing that you should note about this distribution is that it's a geometric distribution. And geometric says that there's independent trials. Okay. Okay, and I'm going to erase that because that's not commonly listed. But independent trials, that's used because the probability doesn't change from each trial, each toss of the coin, or each outcome. Okay, so that's an instance of the geometric. Here we have x, the desired number of successes, and here there is a fixed number of trials. And if we look in the density function, the fixed number of trials is n. So fixed number of trials is yes, listed as n. And I'll use a lowercase. So the mean is n times p. Okay. And since that went off the screen, it affects my formatting, so I'll just say yes, and the fixed number of trials is equal to n. So this is the formula, the density is what's called a binomial distribution. Here it's the number of desired successes out of n. So out of n was left off, and it commonly is, so it's out of n trials. Okay. Now, here our next one, we have our next scenario. Our random variable that's always given us to the problem, it's the number of desired successes. And I'll say that's equal to r. So we could have more than one success, so we could have 3 successes, and you might have to say what we want is we want 3 heads to land when tossing a coin. It's not clear how many trials there are. So here the number of trials should be no. Oh, I see. So this one is the number of desired successes, and that's out of n. Okay, so here we do have a fixed number of trials, that is n again. And I'm going to leave the out of n because that's commonly left off. So here, this is the hypergeometric. Okay. And there is a fixed number of trials. So that is a big distinguishing, because when we look at the hypergeometric and the binomial, they both have the same fixed number of trials, and they both have the same random variable. What separates these two is that there is not a fixed probability p of success for each trial. So this is a very big one. So no, whereas this one's yes, right? So that allows us to distinguish between binomial and geometric because they're very similar. In fact, students commonly confuse these two. Now on the hypergeometric, there is not a fixed probability of success P. An example of this might be that there's a population of 20 individuals and 12 of them have a trait of interest. So the probability of selecting one individual on your first sample is going to be 12 out of 20. But for your second sample, the probability goes down by 1. There's now only 11 people in your population with the characteristic and a total of 19 to select from. So the probability changes for every single trial here. Okay. Now on this next random variable, we have the number of trials until R successes. Okay. And here, this is very similar to geometric, and this was the example I was about to give you. So you're tossing, you want 3 heads, and that's your successes, 3 successes, and it's not clear how many times you have to toss the coin to get 3 heads. So there's not a fixed number of trials, but the probability P of success remains the same for each toss of the coin. Okay, so this one is going to be negative binomial. Okay, and this distribution, the last one here, X is the number of successes per unit. That unit's often time, but it doesn't have to be. P is not given in the problem, so it doesn't really have the same feel of the other problems. But what is given is this K, the mean. This is often sometimes a rate, or it's a mean, or it's an average, all of those things. So I'll just say that. Okay. And this one is called the Poisson distribution. And K is needed in the density function. So the rate or the average value is given, and that value has a units of successes per unit time. So K is very important to identify. Now, this last line we're not going to cover today, but I just want you to know that there are other distributions out there that are discrete. Okay. So now let's test that. Let's try and recognize some of these distributions. So I have a game for us to play. So we're going to play a game of Jeopardy, and we're going to name the distribution. That's going to be the hard part. Okay. And then we're going to calculate the probabilities in question, and we're going to calculate the probabilities in question with R. Okay. So our life is going to be easier because we don't have to do any hand calculations. Okay. So here's our first game of Jeopardy. We have a shipment of 50 parts. The company has accidentally included 7 defective parts. What a shame. Now, there's an inspector for the shipment, and they randomly inspect 5 parts because inspecting 50 is going to take the whole day, and they have other things to do on their time. There's lots of shipments coming in. Okay. So they want to know what are the odds that the inspector finds exactly 2 defective parts. What is the probability that there are between 2 and 4 defective parts found? Okay, so one of the things that we need to do is we need to figure out what distribution to use. Like, that's critical in this problem. So the first thing I'm going to do is I'm going to define x, which is my random variable. X is going to be the number of defective parts. And now I'm going to ask, well, how many defective parts? Defective parts out of how many? There's a sample of 5. So there's a sample of 5, so I'm going to say out of n equals to 5. So let's get this straight. there's a fixed number of trials, 5. So if I go back to my table here, I have a fixed number of trials. I need to decide, is this a binomial? Is this a binomial or is this a hypergeometric? Because I've narrowed it down. There's only 2 distributions with a fixed number of trials. So here it's critical to recognize, are there a fixed number of trials for each of these? Because, hey, look, that's what distinguishes this problem. Okay, so let's go back to this. Notice there is not a probability, a fixed probability of success. In fact, each trial is dependent. Note, probability of success, probability, let's say, and I'm going to call success defective on the first sample. Well, what is that? There's 7 defective out of 50. So, sorry, 50. Probability, and this is not equal to probability of success the second trial, which would be 6 out of 49. And there is this one thing, given success on the first trial. That's equal to 6 out of 49. And because this is not equal to, I know that I don't have a fixed probability. Okay. Red on red is a bad choice, so let's do that. Okay. And if I want to compute this in R, I'm being asked to compute, so there's 2 scenarios. One, I'm being asked to compute the probability x equals 2 here. And oh, and by the way, we need to decide that. So hence, x is, well, let's look at the table. It's binomial or hypergeometric, but we said there's not a fixed number of trials, so it's hypergeometric. That's our choice. X is hypergeometric. Okay, so that's very hard to read. X is hypergeometric. There we go. Probability x equals to 2. Well, I want to compute this in R, so let's go to R. So here's problem number 1. It's a hypergeometric distribution. I want to compute probability x is exactly equal to 2. So what I enter here is the desired number of successes for x, that's 2. I have 7 defective parts, and I have 43. That means I have 43 working parts. Then the other thing that I need to specify is the sample size. So I put in 5. That's the sample size. And if you weren't sure how this works, I could type this, d hyper, and you'll get all the information. I had a spelling mistake, so it comes up, all the information comes up right here on the commands on how to use it. Okay, so if I want to compute this probability, it's equal to 0.112. Okay, so let's copy and paste that into the document. And that's our solution. Okay. Okay. And that way, if you copy and paste this, you're going to get something that doesn't complain to you. Okay. Okay. Now, if I'm going to calculate probability, it says x is between 2 and 4. I can do this. X, and let me write this in nice math mode. So I'll do equation, and I'll put in 2, and I want the nice less than or equal to x less than or equal to 4. And I need to compute what that number is. Well, here's one way I can do it. I can add up the probability of 2 right here. I can add up the probability of 3. I can add up the probability of 4, right? And I can add that all together. That's 0.138. Or I can use the cumulative distribution. This is the probability x is less than or equal to 4 minus the probability x is less than or equal to 1. So probability x is less than or equal to 4 minus probability x is less than or equal to 2. And that's what I'm calculating here. I'm calculating that, and that cumulative part is represented with this p instead of the d. Okay, so I evaluate that, and it's going to give me 0.138. What a surprise. Okay, so 0.138 is my answer. 0.138. And if I want to do this in R, I do that. Okay, so we solved that first problem. Okay, now let's try and do another one. After all, there's lots of distributions to choose from. Okay, we have another game of Jeopardy. And here's the second problem. It says a vaccine for the coronavirus is being tested in 10 patients. The probability that the vaccine cures any individual patient. So remember, this is a big assumption, but we're told to assume it. So let's go ahead and assume it because we need it. The probability of it cures a single individual, which is what I'm calling a trial here, is 60%. The vaccine will be released to the public if 8 or more of these individuals are cured. What is the probability the vaccine will be released? Okay, so the first thing we need to do is we need to determine the distribution. So I'm going to write down my random variable. X is going to be the number of cured individuals. And here, out of 10, there is a probability of success, which is the cure, for each individual is 0.6. So here we have a fixed probability. Each individual's cure does not depend on the other. So if I am cured, it doesn't mean you're cured. Independence, right? And that's big for the binomial distribution. Okay, so if I go back here, X is a number of successes. I'm calling a success a cure. There's a fixed probability of success on each trial. And I have a fixed number of trials. So the only one it can be is this binomial distribution. And I use this formula. But instead of calculating what that number is, I'm going to use R to do it. Okay. So one thing we should write, so X is binomial. Okay. And that is big. Okay, X is binomial. So if I want to solve this problem in R, it asks, what is the probability the vaccine is released? It's asking me to calculate this. Probability X, and I guess I will do the fancy symbol, so insert bigger than or equal to 8. And I want to figure out what that is. Okay, so we'll go to R. And it says problem 2, this is for the binomial. And here, this p binomial, that's the probability of 7 or less. So 1 minus that is the complement rule. So right, probability x is bigger than 7 is 1 minus probability x is less than or equal to 7. Okay. And by the way, probability, since x is discrete, probability x is bigger than 7, that's the same as the probability x is bigger than or equal to 8. Those two are equal. Okay. And if I want to calculate this, I can use this command. I'll use the complement rule. And remember, this says lower tail equals true. That's the default. So even if I didn't write that, it still gives me the same answer. So that's 0.167. And if I have lower tail equals true, is still going to give me 0.167, whether I have that specified or not, because that is the default. Now there's another option. I can change that to false, and that means I'm computing the probability x is bigger than 7. So it does the complement rule for you. Okay, so that is again 0.167. Now, if I calculate, there's another option, which is I can calculate the probability x is 8, plus the probability x is 9, plus the probability x is 10. So let me just go back here with this binomial. So at this number here, 8, that represents the number of successes. 10 represents the total number of trials, which is 10, and 0.6 represents the probability of success. Okay, one thing to remember is what's called success is relative. Okay, so if I compute that, again, I get 0.167. And here's how we could do it as a series, since it was talked about so much as in Calculus 2, is I can instantiate this variable to be 0, then I can add a number to that variable each time in a for loop. So if I do a for loop and I print what that number is, I'm going to get 0.167 again. And what that does is it adds up. All that's happening here is that this variable k is ranging from 8 to 10, and I'm adding all of them up. So I'm doing exactly what's done in this line, just in a for loop. Now that would be very advantageous if I had something that went beyond 10, like maybe I had to add up everything between 8 and 800, or 8 and 100. But you won't be asked to write things like this too much in my course, because these commands are built in with this p binomial. Okay, in fact, this one is the one that I'm going to write down. This p binomial right here, 0.167. Okay, 0.167. And if I want to do that in R, there's the command. Okay, now let's go on to continue this. Just going back to R real quick, the binomial distribution, I just thought I'd give you a histogram of it. So if you were asked, given a plot of data and you knew it was discrete, this is what the histogram would look like. So it's nice and bell-shaped and symmetric, and this value right here happens to be the average value, which is 5. It's n times p, right? It's listed in that table. Okay. So the average number of successes would be right dab smack in the middle. Okay. N times p, so it'd be a little bit bigger than 5. Okay. Now if I change this value or I change this value, the 0.6 or the 10, it'll of course change what the histogram looks like. If I have 0.1, it's highly unlikely to have a success. I'm going to see something that's skewed. And in fact, that's what we see here, right? So we would see a lot of non-successes. Okay. Okay, so I might have spoiled the next problem, but let's look at it anyway. So it says in a certain geographic locations, death occurs at a rate of 9, and I'll specify individuals per day, okay? Because units are very important here. I want to calculate the probability there are 7 or more deaths in a week, 70 or more. What is the probability there? And I'll change the grammar, are exactly 70 deaths in a week. Okay, so we need to figure out the distribution name. X is the number of successes. And here I'm calling successes deaths per week. Well, have we seen something that emphasizes the per unit before? I have no probability of success given, okay? And here, this Poisson one says probability of success is not given. And it also says there's not a fixed number of trials. Like, could there be 100? Could there be 1,000? Can there be an unlimited number of deaths in a certain area? Well, quite possibly, but it is limited by the number of individuals. But the number of individuals living in this area is random, right? So the Poisson seems like a good option, and it says K, which is the rate or average, is what I should put here. So I'm going to go with the Poisson because, well, if I look at these other ones, the only other ones without a fixed number of trials are going to be the negative binomial, the geometric, and I don't see anyone. There's only one other that doesn't require a fixed probability of success, which is the hypergeometric. But if I were to look at this, it requires a fixed number of trials, and I just don't think that I fall in that situation. So I'm going to do the Poisson here. Okay, now let's go back to my table, to my slide. Now, I want to emphasize the unit here, week. I'm giving a rate. This is like the average. Like if you were to compute this, you get this by taking an average. Okay. This is telling me that K is going to be 9, and I'm going to shorthand this, individuals per day. Okay. And if I want to figure out what this unit is, well, I need this unit to match. I need that to be per week. Okay. So what I need, and maybe instead of individuals, I'll do deaths. 9 deaths per 1 day. So what I need here is I need not 1 day, but I need 1 week. And I don't know what that number is. But I do know this. What if I multiply top and bottom by 7? So I'm going to do 7 times 9 deaths per 7 days. Well, 7 days, that happens to be the right unit here. That translates into 1 week. So I'm going to have that many deaths per week, and that number happens to be not a question mark. I can figure that out. That's 63 deaths per 1 week. So that is the value of K. Now, this was before we do anything in R. So we need to figure out X and this, K. So now if I'm being asked to calculate probability X is equal to 70 deaths a week, we can do that. So here I'm going to use the Poisson distribution. The Poisson distribution looks like this. I put in my lambda, that's the 63, and I have the desired number of successes. That's the d Poisson. So that is what I'm going to calculate. And that's 0.03. And that's how I figure it out. Now if I'm asked to calculate the probability x is bigger than 70, and I need the right symbol here, so I'll just steal it. X is bigger than or equal to 70, so I gotta do the equation insert here. I can calculate this in R, but notice this is the same thing as probability X is bigger than 69 deaths. Okay. And what I'm going to do is I'm going to do the complement. So one thing I could do is that this by default is the cumulative. By default, this is going to be equal to probability of 70 or more is going to be equal to 1 minus the probability X is less than or equal to 69 deaths. Okay, so that's what I calculate here. I use the complement rule. And I do this 1 minus this command, and that's the cumulative. So that'd be 0.204. And this is the command that I'd execute in R. Okay. And those are my answers for the Poisson distribution. So I hope that you are getting the sense that the hard part is not actually calculating it, but it's figuring out the commands in R. I mean, it's figuring out which distribution to use, other than just being comfortable with the commands in R. Okay. Now, let's move on. So here's our fourth problem, and it says a flooring expert. Oh, before I move on, I had a histogram here, and this is the Poisson distribution. So it says it's highly, that most of its observations occur before the mean. Okay, so it's most likely that probabilities occur before the average of 1 here, because I have lambda equal to 1, then they tail off. Now this does change shape, so if lambda was 100, it'd look like this, and it looks more symmetrical here. Okay, but if lambda is a small number, it has that tailing quality. And notice that's still true here, because most of them, here's a 100 down here. Here's 100 right here, that's the highest probability. And things are slightly more likely to the left. Like if I go to this one versus this one, it has a slightly higher probability. If I go to this one versus this one, it has a higher probability. And that's always true. So probabilities are more likely to be below the average than above the average. And that's a quality of the Poisson. So really, I'd like you to keep that first histogram in mind here. Okay. Okay. Now, here is a situation in which you have tiles and you need to tile a small area. Now, some of the tiles are produced imperfectly, or if you've tiled before, you know sometimes you need to cut them. Okay, it's more likely that you need to cut it than that they are produced imperfectly, but certainly that scenario could arise in which maybe not with tile, but with some product that's being manufactured has imperfections and it has to be discarded, right? Okay, so there's imperfections in the production process, and the probability of an imperfection is 15%, okay, for each tile. And by the way, I've done other flooring before besides tile. I feel like I need to give out a card for a tile for a flooring service here, but you know, sometimes the laminate or the vinyl, the interlocking ones, the interlocking production is produced improperly, and so occasionally you need to throw away a board, a piece of flooring because of the production process. The groove could be can be from time to time misshaped. Okay, and that might not be due to production. It could have been due to packaging or shipping. Just it gets damaged in some way. So you know, just imagine that scenario. But in addition, more commonly, when you cut the tile, you can improperly, or not the tile, but the interlocking flooring, you can cut it incorrectly, and so you'll need to use another piece. Okay, so remember, I'll teach math. I'll teach math for less than anyone else. Okay, so the amount of flooring that you should need is 25 tiles, or say 25 square feet. Each tile is a square foot, and what's random here is the number of tiles that you're going to need. Okay, because it could be that you have 25 tiles, but when you pull your first 25 tiles, one of them or two of them or five of them could be produced imperfectly, and you don't have enough tiling. So of course you're not going to quit right there. You're going to go and get more tiling until the job is done. So the question is, what's the probability that less than 30 tiles are needed? That's what's random. So here, x, what's random, is the number of tiles needed for 25 successes. Okay, so right away it sounds like the number of tiles needed, it could be more than 25, but it's not specified. You could be really unlucky here, and you could need a lot of tile. So here, it doesn't sound like there's a fixed number of trials. So if I don't have a fixed number of trials, one of them is the geometric, one of them is the negative binomial, and one of them is the Poisson. But notice I have a probability P of success. So probability of success, well, probability of an imperfection is 15%. So it's going to be 1 minus 0.15, it's 85%. Okay, that's your probability of success. Okay. Now, if I look back here, the geometrics is the number of trials until the first success. I don't need one success, I need 25 successes, and I have a fixed probability P. So I think I'm in the negative binomial situation here. Number of trials until 25 successes, I have a fixed probability P. There's not a fixed number of trials, and just one thing that should be noted is that it's assumed each outcome is independent. We're going to need to assume that. Okay, so I should say what x is. Well, we just determine what it is. It's this negative binomial. Okay. Okay. And that was the important part. That was the hard part. X is negative binomial. So I want to compute this in R, and R is going to be slightly different. In R, what the random variable is the number of failures. And let me call that Y. So if I'm going to be asked to compute the probability, the number of failures is less than, and let me just steal, okay, so I'll go to the math and the insert and the equation, less than or equal to 30. Well, if my random variable in R is counting the number of failures and I need 25 successes, that's saying Y is, and let me steal this right here, less than 5 failures. So if I have 30 trials, that mean, and I need 25 successes, that means I have 5 failures. Okay. And let's compute this in R. So in R we have this negative binomial, and if I didn't want to know how the negative binomial works, I can do that, right? Since I want the probability of 30 or less, I use the P. If I want the probability exactly 30 tiles are needed, I use the D, negative binomial. So this P negative binomial is that, okay? So keep in mind, if I was to ask a different question, is going to be a different command and a drastically different answer. Okay, so that's how I do the command in R, and it's equal to 0.711. Okay. Okay. So this is the command in R. Okay. And keep in mind, I didn't put in 30 there. I put in 5. Okay. Okay. So now here's our last problem. So here's problem 5. It says each time an electrical component is turned on and off, there's a 1% chance of failure. Assume each trial is independent and calculate the probability that the component can be turned on and off more than 200 times. So here I have X is the number of trials until it can't be turned on or off, which means it has to fail. And it can't fail more than once, because once it's broken until the first failure. Okay. And so when I look at this number of trials, that's in my random variable. It's not fixed. So there's a fixed number of trials, no, 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 but I need the first success. This one is Poisson. I don't have an average or a rate given. I have a probability. And I'm going to go with a geometric here. Okay. So X is geometric. Okay. Now, I'm being asked to calculate the probability X is more than 200. Now, if I was to use this, I could write it out. This would be a sum. And this is something that we could do with calculus. So if I was to do this, I need this summation. I also need a nice subscript. So insert equation, and I'm going to do a script. I need a top and a bottom. And the first subscript, I need a nice infinity here. Okay. So kind of frustrating, right? So I'd like a nice infinity there. And this would be from k equals 201, because that's the first value of x that's bigger than 200. And I need that nice summation. Okay. And maybe, here we go. That's the one I wanted. So 201 so let's restart all of that. Well, I gotta put in these nice little symbols here. To infinity. Very annoying. Well, one thing that we need for the geometric is probability of success is what we call failure. Success is failure. Okay, so it's all relative. The probability of failure is 0.01. And that's going to be 1. Okay, 0.01, then times point, and I need a nice little operator here, script, 0.99 to the k minus 1. Okay. And this has a nice little name to it. This is a geometric series. And we know the sum of a geometric series. Okay. This first term is going to be 200. And I need that 0.01 times it. Now my second term, when k is equal to 202, this will be 201 plus 203 plus, it keeps going forever. But we can figure out that sum from the geometric series. In fact, it's going to be this. Okay, and here, one over 1 minus 0.99. So in fact, it's just 0.99 to the 200. Then we need to figure out what that is. .134. So about a 13% chance that this component works for more than 200 switches. So I wouldn't count on it. So there's an alternative here, or we can use R. Okay. And if we do that, we're asking for the probability that there are going to be 30 or more, okay? And what we need to calculate is this 1 minus p of this geometric of 199 of 0.1, and that's 0.134. We could also do, so this would be, I put this command right here, because if you were asked to calculate the probability of exactly 200, it would be this command right here. Okay. And so this is what we do in R. Okay. So this is equal to what we calculated in R was this. Oh no, and now I've got the swirly circle of death. Okay, so I'll just get out of that and go back to the PowerPoint. What we have is this, okay? And that was the geometric distribution. So we've gone through an example of every single distribution here, and I just put this other because I want you to know that there are other distributions. But hopefully this helps you to recognize which distribution to use when, because that's a major part of your homework. And I hope these commands in R, if you want to use them, they're slightly different. The random variables for some of them are slightly different than the ones listed in your book and on this table. But if you want to use them, you can use them in R rather than calculating them by hand. Okay, well, thank you very much.